This lecture is on understanding, calculating, and interpreting a Pearson correlation coefficient. It is a critical starting point for our studies because it demonstrates a systematic way to account for the variation in two variables in which we are very interested: a dependent variable whose variation we seek to explain, and an independent variable whose variation we hope to utilize in order to better explain the dependent variable's variation. Here's more detail on how correlations work. The calculation is intended for two variables measured at either the interval level or at a multi-categorical ordinal level. As a rule of thumb, at least a half dozen categories. The correlation calculation leads us to a quick analysis of the strength and direction of the relationship between the two variables. And we should understand a fundamental fact about correlation. It measures association, not causation, between two variables. All we can establish is a relationship, and we cannot determine if one variable is causing the other to be affected. Carl Pearson invented the Pearson correlation coefficient, hence its name. He was a 19th and 20th century British statistician, mainly working in the field of biology. Pearson also invented the standard deviation, which is a fundamental calculation for inferential statistical analysis. It also plays a role in the correlation coefficient calculation. To understand correlation better, we need to start with its close cousin, the covariance calculation. The formula looks like this. Covariance equals the sum of the products of the deviations of each data value from its mean value divided by the total number of cases minus 1. In the formula, x sub I equals each case value for variable x, x bar equals the mean value for variable x, y sub I equals each case value for variable y bar equals the mean value for variable y, sum is the summation of operations in the numerator, and n is the case total. The idea behind covariance is to create a summary measure that can show if variables vary together or not. If we can unpack the formula for a moment, we can see that if the values for the variable x are consistently above the mean value, and the values for the variable y are also consistently above the mean value, then there will be a highly positive number calculated for covariance. If the values for x are consistently above the mean value, and the values for y are consistently below the mean value, then there will be a highly negative number calculated for covariance. If there's no consistency to when the values are above or below the mean value for x and y, then the covariance value will be relatively small. We can calculate a brief example of covariance to see how the formula works. Here is the data set. It is a small sample of countries around the world, randomly selected. The two variables are gross domestic product per capita and a measure of democratic performance from Freedom House, a well-known democracy tracking NGO. The range of values for GDP per capita is from 0 to infinity, though the practical bound is slightly above $100,000 US, with higher dollar values indicating a wealthier country. The range of values for democracy is from 0 to 100, with higher scores indicating better democratic institutions and behaviors. There are more than enough categories in the democracy variable to allow it to be analyzed through correlation calculations. I will lay out the steps using tables, but first I want us to look at a scatter plot of the data. The x or horizontal axis is GDP per capita, and the y or vertical axis is democracy. We can see that the linear trend line is sloping downward from the top left corner of the scatter plot to the bottom right corner. This is visual evidence of a negative relationship. Higher levels of GDP per capita are associated with lower levels of democracy. Again, we have the formula for covariance, to which I will be referring in the next few slides. In talking through the calculation for the covariance formula, we start with the top left portion of the formula, where the mean of the x variable, GDP per capita, is subtracted from each case value for GDP per capita. You can see that there's a large range of values, from $6,976 in Samoa to $70,089 in the United Arab Emirates. The deviations from the mean value of $23,456.43 in these sampled countries are quite large. The deviations from the mean value for democracy in the sampled countries is smaller due to the smaller spread of values from 2 in Turkmenistan to 81 in Samoa. We make that democracy calculation next. After that first part of the formula is calculated, we have to multiply the deviations from the mean for the x and y variables. Which we do. And we wind up with the following products. We then add up the products of those deviations and divide the sum by the number of cases minus 1. Thus, we end up with a covariance of 337,577.1. This extremely large covariance value does not tell us as much as we might imagine it does. The main reason the number is large is because the values for the variable GDP per capita are in the tens of thousands. In fact, covariance values will always be larger when the typical values for the variables are in fact large. All covariance can tell us is the direction of the relationship. If the covariance calculation is negative, then for each case, values for one variable that are above the mean value are associated with values for the variable that are below the mean value. The correlation formula corrects for this, and corrects for it by adding the standard deviation, which is S sub x for variable x, and S sub y for variable y. This correction standardizes the calculation, and in fact is very much akin to a z-score that we had calculated in the POLS 298 course. Since we standardize the deviations from the mean value by using the standard deviation, we thus constrain the range of values for the correlation coefficient and are thus able to interpret the strength of the correlation as well as the direction. Again, I have the correlation formula right here, and we will walk through this with the same data set that we used before. The steps are very similar. We again are subtracting the mean value from each data point for our variable x, GDP per capita, and our variable y, democracy. We're adding another step, though, on top of what we do for covariance. We're dividing those deviations from the mean value by the standard deviation for x and the standard deviation for y. Standard deviation for x is 21,803.36, and the standard deviation for y is 29.57. And the results of those calculations are presented in the table. Then we multiply those standardized deviations from the mean value for our variable x and for our variable y. You can see the values are much smaller than the covariance values. This makes the calculation be more manageable as well. We sum up those products, and the sum again is a relatively small number. We divide by the total number of cases minus 1, and we wind up with a correlation, and the correlation is represented by the little r. So that means Pearson's R, or Pearson's correlation, minus 0.53. So that is the result of the calculation. What does this mean? Well, we can interpret both direction and strength. Positive direction means that has values of x increase. Values of y also tend to increase. Negative direction is values for x increase, values for y decrease. And if it's neutral or near zero calculation, then there isn't any discernible direction, and any line that is attempted to be drawn tends to be a relatively horizontal flat line. Well, we can see from our calculation, to go back for a moment, minus 0.53, it's definitely in a negative direction. And if we can go back through the scatter plot, go back to the scatter plot, indeed it looks like it's a very much a negative direction for this relationship. So that calculation is not surprising. This is a rough guide for interpreting the strength of the correlation. And our correlation calculation of minus 0.53 falls under the strongly negative correlation category. So we can say that the correlation is both negative and strongly negative, and that there is, again, a definite direction downward in the correlation calculation. So, just to summarize what we've talked about, the correlation of negative 0.53 is a strong negative correlation. As the values for GDP per capita increase, values for democracy decrease in this sample, which is small, just 7 countries, but sampled for the year 2019. I hope you've enjoyed this presentation. Feel free to go back through it, and have a nice day.